Hello everyone, it's October 26th. Alright, we're on a very bad streak. Let's see if we can reverse it today. Alright, so I think I've done this before, reverse a binary tree. Oh no, I haven't. Okay. Given the root of a binary tree, invert the tree, return its root. What do you mean by invert? So, everybody left and right. So don't we just swap left and right? So we got a root, right? And then we swap, and then we swap these two. Yeah. Alright, I think this should be enough. Well, that's what I said yesterday. And then halfway through I realized, nah, that's not enough. So let's see what we have today. Yeah, looks straightforward enough. Alright, let's see. Okay. Alright, so when I invert, right? So we say if root, right? I just say if root. If not root, return none, right? Otherwise, we're gonna say invert self.invert tree root.left, self.invert tree root.right, and then root.left root.right equals root.right root.left. Return root. Alright, let's try this. I think this suffices. Let's see. Yep, I think so. Yep, alright, so I got it today. This is pretty easy, right? Pretty easy. Oh, there's nothing to say. I'm just gonna go as ON solution and 32 milliseconds. 76. Let's write something here. So we firstly we invert the left and the right subtree, and then swap them. Yeah, that's it. That's all I want to say. Okay, so we're done. Let's roll another question then. Let's roll another one. All right, again, we're gonna roll let's roll a medium. All right, let's pick a medium. Uh-oh, I cannot do this one. All right, that's fine. That's fine, I'll do it again. Pick one again. All right, let's see. Okay, let's do this. Group the people given the group size they belong to. Okay? There are n people that are split into some unknown number of groups. Okay? Each person is labeled with a unique ID from 0 to n minus 1. 0 to n minus 1, okay? You're given an integer array group sizes, and group size I is the size of the group that person I is in. For example, group size 1 equals 3, then person 1 must be in a group of size 3. Return the list of groups such that each person I is in a group sizes I. Each person should appear in exactly one group, and every person must be in a group. If there are multiple answers, return any of them. It is guaranteed that there will be at least one valid solution. Okay, so we have all these people: 0, 1, 2, 3, 4, and 6. They all need to be in a group of 3, and then this one needs to be a group of 1. So the first group is 5. The size is 1. And group size 5. The second group size 3. And then 1 needs to be, 0 needs to be in a group of 2, 1 needs to be in a group of 1, and then needs to be a group of 3, and last one group of, okay? So we know, what we know is the group sizes, right? So we have group sizes, so I know the size. So let's say if I have a 3, it means I know this person needs to be in group of size 3. So I can, but there could be multiple groups, right, of size 3, of size 1. Okay, so I can say size 3, dictionary, right, size 3, and it can be a list, okay? So the list will be a list of lists, right? The first one we put in here, and the second one, I'm looking at this one, 1, so we go 1 and 2, and then we had another one, right? And then we go into 3, and then we find out the first group, so we add a new group, that's 3 and 4. Yep, I think that shall suffice, and eventually we're gonna just, we can chain them. I have a strategy for this. Oh, let's try it. Ha! Es una muy buena oración. Sí. Muy buena oración. Pero no es Jimbo. Jimbo le gusta modernos. All right, let's do this. So we want, let's do a import. I think I need a default dict, right? So we're gonna say groups equals default dict list. Well, actually it's a list of lists, but that's fine. So we're gonna say for IG in group in enumerate group sizes, right? Group sizes. So G is group size. So we're gonna say if G, right? If not groups G, then groups G dot append I. Else, if group G has something in it, right? Then we say if groups G minus 1, and that's length. If length of this is smaller than G, then we say groups G minus 1 dot append I. Otherwise, groups G. Okay, so we are repeating ourselves. So here's what we're gonna do. So we're gonna say if groups G, right? If groups G and len groups G minus 1 is smaller than G, then we append. Elsewise, either group G has nothing in it, or the last element, the size is equal to G. That means we need to create a new group. Then we append this. I'm going to return. Let's try using chain from iter tools import. What is it from collection or collections? I forgot. From collection, yeah, it's collections. So let's go chain. Let's try chain. So how do we want to chain it? So basically, we need to chain. Let's say list chain. Chain what? V for V in groups, Like that? I'm not sure. All right, let's try it. I think that's how you use chain, right? All right, test cases. Well, actually, test case, I think it should be fine. So we have this, and the answer is this. Right? Next one is this. The answer is this. Okay. So we have group sizes. This is group, the people, group sizes. I just run it. Nope. Oh, the values. I forgot the values. No, that's chain. Hold up. I think we need to deconstruct it. Cannot be in comprehension. Wait. It cannot be in the value itself. Hold on. The value itself is a list of lists. Oh, I cannot cannot be used in comprehension. I cannot deconstruct it. Then I cannot chain. I mean, I am chaining. Right? Let's see. I am chaining. Look, I am chaining. But, oh, hold on. What if I do this? Nope. Wait, what the heck? It's a list of Oh. So when I chain, what happened when I chain? I'm chaining this and this. How does chain work? No, this is not related to it's a tools. Yeah, I'm just curious. I never really understand chain. Is this and this will return this. So I need to chain hold on. Make an iterable that returns elements from the first iterable until it is exhausted, then proceeds. Okay, so what is our return value? Our return value is a list of list, right? A list of list. So in order to chain it, we need to deconstruct it. Yeah, I think I need to do. I think we need to deconstruct here, right? Yep, that's it, and it's correct. I mean, we'll say it's not correct. We can sort it, right? We can say sorted res lambda key equals lambda item len item, right? We can do len item. Oh, even that, yeah, that should be sufficient. So I'm going to sort on this and sort on answer. There we go. Okay. Yeah, that is how you use the chain. So the chain, you have to pass in each individual variable into it. So if we have done the comprehension, we need to deconstruct the comprehension. Okay, use example. Yep. All right, let's try this. Okay, we pass. So that's not that hard. we use a dict to keep track of each group of a certain size, right? If during iteration, right? During iteration of group sizes, if the value, if the current person can fit in one of the group, can fit in the last group of the dict size, we add the person there. Otherwise, we create a new group, right? We create a new group within dict size. This runs in ON and it gives us 76 milliseconds. 84. All right, I'm going to take a quick look. I don't think there's much to discuss. Greedy hash map. Enumerate count size. Ah, I see. I think I know. So for SL, count the items. For I in range 0 to this. Oh, land this with this. Nice. Good solution. That was a long time ago. All right. Yeah, I like this problem. Okay, let's roll another one. Let's roll another one. Wow, that'll be the first time. 3 times, 3 questions. I'm gonna roll a third one. All right, let's see what we're gonna get. Super pow. Not done this before. People don't like it. All right, that's fine. Let's try this. What do we have? Your task is to calculate a to the b mod 1337, where a is a positive integer and b is an extremely large positive integer, given in the form of an array. Ooh. B doesn't contain leading zeros. B length of 2000. Oh, what is this? What is this? So basically 1337, is that a prime number? Is 1337 a prime number? A prime number. No, it is not. It's divided by 7 and 191. Okay, wait, really? That's not even a prime number? That's a weird question. 1337. No, 7. Divided by 7 and 1. Is 191 a prime number? Is 191 a prime number? Yes, 191 is a prime number. So 1337 can be divided. 1337 can be divided 7 times 191. And we want to find the mod. A to the b power mod 1337. Well, of course, if it's smaller than 1337, then it's by itself. Because 1 is going to be this, right? These are like the special cases. But A can be any of these values. A is this value, B is this value. So it's a mod, so we gotta have, wait, what? Is there any property of modding? Like, if A mod 1337 Why 3? I just pick another value. Let's say mod 2, right? Mod 2. So if 3 mod 2 is 1, right? And 3 to the power, any power mod 2 is 1. Are you telling me that any value, if its power, it just times itself, mod another value, can we prove it? It will be the same as this value mod. Well, if it's bigger. If it's bigger than 1337. Let's see. How would I prove this? I'm not sure, right? So let's say A, that's a mod M, right? A will equals to Q times M plus R, right? So that's A mod M equals R. A equals Q times M plus R. How about A squared? So A squared is MQ plus R squared, which is M squared Q squared plus 2MQR plus R squared. So it equals M times MQ squared plus 2QR plus R squared. Okay, so A squared is R squared, right? So if we want to find A squared mod M is equivalent to find A squared mod R squared. How do we find A squared mod R squared? Well, A squared mod R squared will always be R squared, right? Right, no. What are you talking about? A squared mod M is equal to A squared mod R squared. Yeah, it is. It's mod R squared. Which is true, right? With mod R squared. So, and if M is huge, if M is big, right? If M is big, then it will always be R squared. R squared, if R squared is smaller than M, right? If R squared is smaller than M, then R squared is the remainder. So if we keep doing this, right? If we keep doing this, at a certain point, R squared will be bigger. And that's when, so basically the question is to find the remainder of A mod 1337, and that value will be smaller than 1337. So it's that value going for all these power and mod 1337, right? Okay. So then we reduce the problem to something smaller, to a gigantic power, and that might work, right? Okay, let me see. A36. So I'm trying to do this one. So what if we do this mod 1337, right? It'll be easier just to do it here. So we have this value, right? Let's say A equals this. A mod 1337 give us 932. So basically we calculate 132 to the power to 200 power. Oh, that is a giant number. And we calculate this mod 1337. That's the answer. But still we have the issue of R to the, so R is smaller than M, right? R is smaller than M, but R to the some power will be bigger than m. What is the relationship between the remainder and this value? Remainder to the power and this value. Let me think. So r is smaller, so r times r. Wait, do we have... No, what if we do it every single time? Well, if we do the first time, the remainder is r, right? And then we multiply r again. So r equals 0 times m plus r squared. I don't know, maybe we shall just go for it. I mean, let's see, can Python handle 2000's power? Oh yeah, I think it's pretty fast. That's pretty fast. All right, I guess that's the only trick. Not sure. 372. I mean, if that is the only trick, then I can see why people don't like this question. Wait, hold on. I got it wrong. 372. Yeah, I feel like that's the only trick. All right, so the trick is r equals a mod 1337, right? I'm gonna say m equals 1337, so mod m, and then we shall return. Oh, we need to make b into a value. Jesus, how do we make b into a value? Can we like a one line to make it into a value? P equals 0, and for B, B, and B, I don't know what to do. Oh, and have to be reversed. For I in range lam B minus 1, minus 1, minus 1, right? And then we say P close equal to BI times 10 to the what power? 10 to the len b minus I power, right? No. Oh, yes. Len b minus I. So len b minus 1 minus I, because the first one is to 1 power, right? The first one is 0 power. So whereas length is 3, and then maybe 2. So 10 to the 0 power, 1 power, and 2 power. So that's P. So now what we have is R raised up to P and then mod M. I don't know. This is a weird question. Yeah, that's the thing. Like if you random, you get hit by these weird questions that you don't even know. All right, this one is 8. Yeah, that makes sense. And this one is going to be 1024. Makes sense. And this one's 1. And having these. This one will be 1. Yeah. And the last one will be, this is a 2 to the 31st minus 1. And 200's power. So we don't do 200 power. We do actually a smaller value, right? So we have AB, superpower AB. Yep. All right, let's try. You know what? I think, I mean, Python can handle gigantic values. I mean, it's possible if we Like, don't do this. Oh, am I timeout? Or did I get something wrong? Oh, do timeout. Ah, so, okay, so that is the challenge. Oh, this one, TLE. Wait, timeout at what step? To the power. The power is too huge. Right, that's 2,000. Oh, it's 2,000. Oh, okay. Yeah. Of course, gonna time out. All right. So there gotta be another trick. So we find one trick. There gotta be another trick. What's the other trick? R times. Hmm. It is R to the P power, right? It's R to the P power. So reduce it to R to the P power. But R to the P power is still too big. Right? It's still too big. So R times R times R times R. And then we need to divide it by M. And we want to know what is the remainder. Okay, how about we divide it in two? I see if it's like its power has anything to do with it. Let's say I know R mod M equals R, right? How about R squared mod M? I don't know. What is R squared mod M? Hmm. R squared. Okay, let's say I know R squared. I know R squared equals, um, let's say MQ plus T, right? So MQ plus T equals R squared. How about R to the fourth? Oh, look like that. R to the fourth is MQ plus T squared, right? Which is T squared. So I think we're applying the same thing, right? So R to the fourth. So hold on. We're almost there. So what do? We are going to so it becomes a problem of R squared, right? Become a problem of R squared. But what if it's not divisible by 2? Well, let me think. So R squared is going to be like this. Or we can do like R to the 3 power. Or R to the second power is going to be like this, right? And I grab a T. And then the whole thing can be written as R squared, so R to R squared to the whatever power, and that's going to be T to whatever power, and times R. Right? So all these things is going to be T to the whatever power times R. Right? So we need to find the remainder of this. Okay. And then I'm going to find t to this power. So we need to find the remainder of this. So that's the new remainder. So we find the remainder of this. Hold on, let me do it again. So a to the b power, right? So a to the b power, we find so a times a times a, and then we find the remainder a mod m. So we turn this problem into r to this much power. Okay. And then when we turn r to this much power, and r is a value smaller than m, and then we do r squared. So it's r squared to whatever power times r mod m, right? And this one is equivalent. But is it equivalent? Because this one will be something m, right? And then eventually will be plus rt to whatever power, right? Times r, and r times, so will be t times this power times r. Or there's no r, so t times this power. So this one will be reduced by half. Reduced by half, right? And then we go here, we do it again. This is the same thing. T is a value smaller than 1337. So this value we can keep going. So eventually we will arrive at a value. So we're constantly bringing it down. So we get the R first, and then we say while hold on. So we need all this, and we have this, right? Now it should be while p. So while p, that's the power, right? And we say final, let's say equals 1, all right? And we say if p is not even, right? Then we need to say fin times r, right? And then what? And then we need to reduce p by half, right? So p, when we reduce p by half, and r shall equal to r squared, so r times r mod m. Right? And let me think again. So that would be that to the to whatever the amount of power times r, right? And if it's otherwise, we just update r. We know it's r to whatever this power, and then r squared again to whatever this power until we're done. Until we're done, there should be fin times. So we return fin times r, whatever r is remaining, and then mod n. Nope. Nope, it's not right. It's not right. Hold on. Why is this not right? All right, power was to the 8th power, right? So it's 2 to the 3rd, right? 2 to the 3rd. So I say power is equal to 3, all right? And 3 is and p divided by 2. Huh? Hold on. So we get R, right? We get R, that's fine. And then we get R, we get a P, right? And then now we're looking at R to the P mod n, right? So I say, okay, that's too much. So what I do, I want to divide it. I want to turn it into R squared to whatever, right? Either maybe a time R or not time R. And if it's R squared, then if R squared is it has to be some value larger than n for this scheme to work, I feel. If R squared is not larger than n, let's just say it's not larger than n, that's fine, right? R squared. So now we say R squared to the 1 times R, right? And R squared is 4. All right, so 4 mod equals 4. How will it come up to, so P is 3, I think we get an R, and then P divided by 2, which will be 1. P is now 1. P is now 1. I think P is now 1. Okay, so the new R is R times R, because I say it's R squared, which is 4. So R is now 4. Now I'll go back. P is 1. And then we do this. And fin is as 8. So here is 8. And P, and it becomes 0. And this line shall not go again. Okay. And I pretty much, because eventually we'll go down to 1 anyway. So this should be just fin. So for 1, this should just be fin. And how about we just go while true, right? And we check here. We say if not P, then we break. There we go. Look at this. This one works. All right, let's try this one. Let's try this one. This one works. This one works, but pretty bad. Pretty bad. Let's see. Can we improve? This one should be fine. Maybe we don't need to do this at the beginning. We can just straight up. Can we straight up just using A? Let's see. If we say, maybe we can do that. let's try this. Let's just don't do this, right? And we simply do A, and A equals A times A. Yep, this one works as well. So we can eliminate one of this. Yeah, this one just look. Can I just put P up there? Let's see, this one shall be faster. So we can reduce one of the mod call. But this is still going to be a big mod call though. Let's see. Anyway, so this is what my solution is. Okay, so this solution. So the insight is that we can reduce the power by 2 at each iteration, right? Which means this means given a to the b, a to the p, we try to turn the problem into a squared, right, to some value, right? Turn to this, depending on whether p is even or odd, we will have a squared to, I don't know, mod m equals to a squared mod m p divided by 2. Actually, I have this divided by 2 times a, and this whole thing mod m if p is odd, or mod if p is even, right? So, and we can continue doing this to reduce the power, right? To reduce p until it is gone. The value, the remaining value, right? The remaining value, and we can just continue to do this to reduce p until it is gone, and then we will have. Then we can compute the mod more easily. So it's O log p, where p is the total power computed from b, right? And this one is pretty slow, 368, 9.8%, 9% ranking, which I feel like is because we do a lot of this. Maybe there's a better way to handle this. All right, let's take a look. Fermat and Chinese remainder. Power called only once. Yeah, I guess there gotta be some math theory behind it. Let's see, what's the 100 milliseconds? Let's just take a look. power a. Wait, what? Wait, what is this? Yeah, this is probably easier to do than the one I. Maybe that can speed it up too. Let's do it here. Yeah, so P equals, I don't want to do it this way, but join str bb for bb and b. So maybe this one will make it a little bit faster. Try it again. Oh, I got to 320. Just gradually, I think I got like 12%. But this just POW AB and 1337. What is that? Like, what is that? Python POW. Read the document. Read the document. Where's the documentation for this? It's a building function. POW. Return base to the power. If mod is present, return base to the power modulo. Oh my god. Oh my god. There is a building function for this. Okay. That's why people don't like it. Well, that's why Python is great, because it has a building function for this. Jeez. Wow. Wow, there's a building function for this. I did not know. Well, now you learned there is a building function for this. The POW built-in function is specifically for this. So basically, we just grab the P, right? We grab the P, and then we return POW A to the P model 1337. Oh, this could be like cheating, right? That's not the purpose. They don't want you to do it this way, but oh, I did not know. Wow, we can do it this way. Oh, I can do it one line, right? We can put this one in here and do it one line. Anyway, math solution. Oh, jeez. Divisor is 7 and 1 and 1, exclusive 1. So judge if A has a divisor, then that 7 and 1 and 1 are prime numbers itself. And here's Euler's theorem. Oh. Phi. Wait, what? Mm-hmm. Coprime. You know what? I don't like this explanation because I don't understand. What's the point of this kind of problem? Modulo exponent. $1337 is a lead upside down. What? Oh my goodness. Oh, that's why 1337. All right, let's take a look at this. Yeah, probably I'll end it. That's just a little bit math time, right? Remainder repeat. Repeated pattern. Yeah, I was on here, but I timed out. Small int. Hold on. For each digit, we can do the above computes a to the fifth and a to the fifth, and then finally. And the step from one to the next can be done like, huh? The recursion. What the heck is this thing? Alright, anyway, I think I'm gonna have to take some time to read through this. So I'll end up here, but wow, we did 3 questions today. That was a record. I'll see you guys tomorrow. Adios.